The topic of today's lecture is pneumatic displacement gauge. The objectives are to learn about pneumatic displacement gauge and also solve a numerical problem to demonstrate how some of the uncertainties that are associated with such a device could be addressed theoretically. So a pneumatic displacement gauge is a device that's used for measuring small displacements that may not be possible to measure using any other devices. A figure of a pneumatic displacement gauge is shown here. There is an ambient pressure PA, and that would cause the flow of air through an orifice and a nozzle. Orifice has a diameter d1 and the nozzle has diameter d2. The measurements that are made are at point 1 and 2, and the workpiece would be a small distance x away from the end of the nozzle of the gauge. So if we consider the system that is also the schematic of it is provided down here on this figure down here, further down. Air is again supplied at a constant pressure P1. The flow through the orifice would go through the outlet of diameter D2. That is actually governed by a distance x, which is a separation between the outlet and the workpiece that as I just mentioned. The change in flow with x will be indicated by a change in the downstream pressure from the orifice P2 or nozzle P2. And there's also an ambient pressure of PA present throughout the operation. This would actually provide us with an incompressible flow, and we use the fundamentals of fluid mechanics to derive some equations and that are applicable to such a device, because having such a device and any reading that we can extract from that device is really not enough for us to perform our engineering analysis. We also need to be aware of the uncertainty that is associated with the measurement that this device would put out, so we can reduce those uncertainty and include those in our calculations and to come up with a much accurate as possible results. So from the fundamentals of fluid mechanics, the volumetric flow through an orifice may be expressed as Ca square root of delta P. This is there are many different variations of this formula in the form of discharge, other forms that are presented in other books, but this is what we would use for this class to drive the equations and that are that is of interest to us. So in that equation, also presented down here, but instead of delta P now we have P1 minus P2 and P2 minus PA. They are presented in the forms down here. In these formulas, C is the discharge coefficient, A is the flow area of the orifice, and delta P is the pressure differential or if you will, change in pressure across the orifice. There are two orifices that was shown in the picture, the schematics that we took a look at. There are one that was pretty obvious, and you've seen it in the figure, and the other one that may not be that obvious is the one that was formed by the flow restriction between the outlet and the workpiece. So if we take a look at that figure again, we are interested in the flow right before the orifice, the obvious orifice here, D1, and right after. So the areas of the first orifice is A1, and the second one is A2. Then the previous equation, we simply replace the pressure differential by a P1 minus P2. We're expanding the equation, and in these cases, it is the P sub A is the ambient pressure, and it is assumed to be constant. So the equation Q is C sub 1, A sub 1, square root of P sub 1 minus P sub 2, or simply what I refer to as C1A1 P1 minus P2 square root, can be arranged as such. Remember, we are after a relationship between the multiple parameters that we have and the displacement x, so that will be our eventual goal. The area of the first orifice that's shown here, it's circular, so it is given as such. And for the second one, we also calculate that as such. So we rearrange the equation for Q. We come down here to pretty much express that in terms of areas, and we call that R as a pressure ratio. This R that's given here, this is a pressure ratio. Is simply a ratio of P2 minus PA divided by P1 minus PA. And we also made another assumption in which we assume that the discharge coefficient C1 and C2 are equal for such a device. So there are certain important assumptions that was made here that are extremely important in our calculations. So there have been some tests performed on the pneumatic displacement gauge. There's a linear and nonlinear range. I'm not going to get too much into the nonlinear range, but two of the folks, scientists or engineers, they test and play around with the device, and they realize that the ratio, area ratio A sub 2 divided by A sub 1 is very linear for a specific range, 0.4 and 0.9. So let's call that an upper value and a lower value. So the 0.4 is the lower range, and 0.9 is the upper. So if you want to do any kind of calculations to come up with a range, we simply plug in R as 0.4 as the lower bound and 0.9 as the upper bound. So as I just mentioned, the area calculations are really based on the shape of the orifice, and the second one is a little bit different than the first one. We express that in terms of the diameter. So we have from here, R is P2 minus PA divided by P1 minus PA. Again, as I'm going to these equations, I'm going to put a red line, red mark either under it or above it, so you know where I am. Then we also have our measurements from the test. In this case, as we've just seen, it's 1.1 minus 2.00. Note that I'm keeping these digits to keep the accuracy and be consistent when I am discussing pneumatic displacement gauge, and that is because the displacement could be measured with certain accuracy. And then d sub 2, this is the diameter of the second orifice, and then d1 is the diameter of the first one squared. Okay, so this is d1 squared and multiplied by x, and this is valid for this particular range. Again, the upper bound would be 0.9 and the lower bound would be 0.4. So the pneumatic displacement gauge is mainly used for small displacement measures. So after we establish our equations briefly, note that I didn't get too much into deriving all these equations. I rely on the fundamentals of fluid dynamics, fluid mechanics, and to be able to actually calculate these equations. I do, however, I'm going to concentrate more on the numerical example that we are going to discuss now. How can we incorporate a given uncertainty in pneumatic displacement gauge into our calculations? This displacement could be associated with multiple parameters, but we are not going to consider all those, perhaps one or two at a time. So in an example that I'm going to discuss with you, there is a pneumatic displacement gauge like the one we've just seen, and R1 is given as 1.10 minus 0.5 A2 divided by A1, and the diameter for 1 and 2, points 1 and 2, the orifices they're given. D1 is 0.030 and D2 is 0.062. Again, I'm carrying all these zeros after the decimal because I want to be able to relate the accuracy and show you the accuracy. In this case, it's 0.062 and here is 0.030. So the supply pressure is 10.0 psig, and the differential pressure P2 minus PA is assumed with a water nanometer, which may be read with an uncertainty of 0.05 in H2O. Remember, this P sub A is the ambient pressure, and that is constant throughout our operation. So there's not much change associated with that. But the uncertainty is with the differential pressure P2 minus P sub 2 minus P sub A, and that uncertainty is 0.05. Okay, it doesn't have any units because the unit would be according to what the readings would be. So it's just a plus or minus 0.05, as you've seen with some of our previous examples that you have solved for as part of your lab book. So we calculate the displacement range for which R is P sub 2 minus P sub A divided by P sub 1 minus P sub A. This is from our equation. Again, we just duplicate the equation here. This is what we've seen so far. Nothing new about this equation that I'm just encircling in red. Okay, so this is the equation that's given. We have this equation, and it's again very important to realize that this is only valid for the range that is given here, the range of R between 0.4 and 0.9. So if you want to do a non-analytical calculations in which you want to calculate the uncertainty, it's pretty straightforward. All you do is you plug in as your R 0.4, you calculate your X. Okay. So if you have R equals to 1.10 minus 2 d2 over d1 squared multiplied by x for this range. And all you need to do is you're going to plug that in using the d1 and d2 that you have, and then you would actually calculate that. So you calculate a lower bound and an upper bound. You take the average. That will be the analytical, the non-analytical uncertainty. If you want to do the analytical uncertainty, then we need to use our partial derivative methods and take the square root of sum of the squares. Again, I'm going to show that to you shortly. So we have our ratio as d2 divided by d1 squared. We take this ratio. Note the square. I often see this missing in calculations that are submitted to me. So we want to make sure that we don't forget about that. Okay, so this is just simply the d1 squared. So 0.062 divided by 0.03 squared, and it would be 68.8. Remember that you should check your calculations or my calculations as we are going through this. So feel free to grab a calculator and go over this with me. So if R is 0.04 in this case, then we are going to have X as, again, we simply replace the parameters with what's given, 1.10, 0.4, 68.8, which is 68.8 here, which is the ratio of d2 over d1 squared. And the rest is given. All we did was we just plug in R as my 0.4. And that would turn out to be 0.0509 inches or 0.129 centimeter. Note again down here that the equation is written out to help out. So in this case, as you can see, we can simply take this ratio and we rearrange the equation. And knowing R, we can easily calculate X. This is the, again, lower bound for X when R is 0.4. And we also can do similar calculations, except this time we are going to put the upper bound R, which is 0.9, and as a result, X would be 0.0145. Okay, that would be 0.0368 centimeter. I expressed both units here to be consistent with our learning objectives. Remember that now every time we want to again calculate the uncertainty in an equation with multiple in an equation with multiple parameters, what we do is we differentiate with respect to each parameter. We keep the rest of the parameters constant, and then we square each of those uncertainty. We sum them up, and then we take the square root of those sum. It's called the square root of sum of these squares. Okay, and it is shown in some books as SRSS, square root of sum of the squares. It is again, as we have seen before, based on statistics, it would really help out to calculate the uncertainty. It would simplify the procedural. So we are going to apply the same equation here, since the uncertainty is given in this case. As you can see here, again, the partial derivative of R with respect to X in this case is really the partial derivative of the small r, not a capital R. Okay, so this is the general form of the equation. Okay, that's written out here. And for the small r, this equation would be reduced to this form. Okay, it's pretty straightforward up to here. I don't think there should be much of a discrepancies so far. So also realize that when we come up with an equation for R, there was a delta P in that equation. And here now, that delta P is given with certain uncertainty. So we call that W sub delta P. It's a not capital. Remember that. It's a small font, W. And this is W sub R. So now we are going to use that equation that was given, and we simply remember this is plus and minus, so it could be shown as plus and minus. We use the minus sign. In this case, we multiply 68.8 by 2 minus 137.6. So the uncertainty in the measurement of P2 minus P1 is then 0.05 times 0.0361. Again, no magic here, which should be 1.805 times to the 10 times to the 10 to the power minus 3 psi, and this is also 12.44 Newton per square meter. So the uncertainty in X is then given as simply this equation, the result of W delta P. We use that again. Let me go back to the previous equation, and I divide that by P1 minus P2. In this case, we already went through the calculations, okay, and we come up as 137.6. Again, I'm going back here. Look at this calculations that we performed here, and this is the number I'm going to use here, 100 minus 137.6. It's going to appear down here, multiplied by 10, and this would be pretty much the results, 1.313 times 10 to the minus 6, which 10 to the minus 6 inches, which is 1.313 micro inch or micrometer, 0.033 micrometer. Okay, so that would give us the uncertainty that is associated with this particular problem as shown, and we show that as W sub X. Now in your lab work, you would use the same form of showing each parameter accordingly. Okay, that brings me to the end of slides. Let learning continue. As always, if you have questions, please contact me. Thank you.